Good afternoon. This is Caroline Hazard with the Jump into STEM team, and welcome to the Round 3 Challenge Webinar 3, looking at field experiences as we talk about the challenge Pushing the Envelope with Wall Retrofit Designs. Okay, so today's webinar will have an agenda where we'll go over a quick overview of the website, what is Jump into STEM, and an intro to our current challenge. I will be referencing previous recorded webinars so that you guys can go back to those and reference those as needed. Our main feature today will be hearing from Matt Waring and Bill Riggs from Viridiant about their field experiences in implementing wall retrofit solutions. So we want to leave plenty of time for them. So what is Jump into STEM? It's a student design competition that we've started this last year in 2018 with Fall Challenge Series to down select finalists for a competition to win internships at the Oak Ridge National Lab or the National Renewable Energy Lab. This is a great opportunity for college students and university students to engage in these challenges, to see what they think about building technology and produce some good ideas and hopefully win an internship. Our main objective is to expand our reach across the nation. We're also looking to cultivate diversity by including more minorities and women in the STEM fields. We also want to connect more directly with universities, professors, and the college professors and university professors in their coursework to try and help them have this platform to offer to their students and hopefully use it as a bonus point or perhaps as a grade in their class. And then ultimately, we want to motivate creative thinking and ideation for advancement of building research and innovation. So this is a quick snapshot of how it works. I kind of went over this a little bit. We start off the challenges with a series of online competitions. Today we're talking about the third challenge in the series. The other two previously occurred this last fall. As we select the winners from each of these challenges, they will then be invited to a final event at NREL on April 12th to the 14th. This is a really exciting event that's going to be held in conjunction with the Solar Decathlon and Design Challenge weekend. So the finalists from this Jump into STEM Challenge series will be able to benefit from seeing how the Solar Decathlon and Design Challenge students are working on their challenges, get involved in networking, as well as be a part of some of the competition activities there. So that's really exciting. And then, of course, the ultimate goal here is to get to the Summer Internship Awards. And so at that final event, the finalists will compete for those 6 slots. All of this information is on our website, jump.ideascale.com. So you should go there to see more. So these are our eligibility requirements. Generally speaking, you need to be a legal resident of the U.S. or the District of Columbia, 18 years of age or older, and a current university or college student. And you can read this on your own as you go through it, but this is just a quick snapshot of what you need to do to submit an idea and be eligible for the internships. I wanted to put this out here so that any of our friends from the universities and college academic departments can learn about how they can get involved. We're looking to make this a modular or extracurricular content for architecture or engineering and computer science departments. We are interested in other departments beyond that, but we do have a particular outreach focus on these 3. So do connect with us if you are interested in that. We're challenging the students on current industry market research questions. These questions are questions that the labs are thinking about and the Department of Energy are thinking about. So these are real world issues that we're trying to address. And so getting the students involved in that is really a key aspect of our effort here. And we're looking to provide reward opportunities for the students, obviously with the internships, and then problem solving as another benefit of this platform, and access to building science content. That's particularly true with today's webinar with our great speakers from Viridian, so that the students have access to what's really going on in a building, and they can use that as they grow and build their career and their future. So this is going to go very fast. Navigating jump into STEM. I've done this before, so if you want to go to how it works on the website at jump.ideascale.com, there is a video there that kind of walks you through how the whole site works. Once you've done that, you can also check out any of the challenges. This is a bit of an older screenshot, but it's telling you about round 1, but there are other 2 rounds are listed here, and this is what you click to see the challenge. Once you click that, you'll get a card that kind of looks like this. Again, this is an older view of a snapshot of the round 1 challenge, but you'll see the round 3 challenge. And you can always scroll down for more information, including access to recorded webinars from previous webinars we did to support the challenge, as well as any additional links to sources of information that might be helpful in formulating your idea. So do check that out. And then when you're done forming your team and thinking about your idea and you're ready to submit, you'll click this button here, and you'll fill out a simple form that looks pretty much like this, where you basically fill in what challenge you're responding to, what your team name is or the title for your idea. You can vote on other ideas that are out there if you like to. You put in a little bit of a blurb, an abstract, if you will, about your idea. And then you can attach, this is an important part, you can, this is the tagging option here, but down here you can attach, you hit browse this file, and you can attach as many files as you want to help support your idea. There is a limit of 25 megabytes, but that's a great way to make sure we know exactly what you're thinking about in presenting your idea. And then you hit submit. So with that, and this is what you get, what it looks like after you've done that, and you're ready to go. So let's do a little bit of an introduction to Matt and Bill. Matt Waring is originally from Richmond, Virginia. He's the son of a single-family contractor and grew up around construction and on-the-job sites. He has worked as both a single-family and a multifamily superintendent. With 5+ years at Viridian, Matt has worked as a technical advisor, project manager within Viridian's multifamily team, and is now serving as the technical director, working with Viridian's in-house field personnel and project management staff to provide rating and construction consultation services to a range of clients throughout the state of Virginia. Also joining us today is Bill Riggs, who was born in Richmond, Virginia, and attended the School of University of Vermont in Burlington. And while studying environmental studies, he worked for a small independent contractor that performed energy audits and weatherization work. Upon coming back to Richmond, he worked for a single-family contractor that specialized in deep energy retrofits. Bill is currently serving as the technical advisor with Viridian and providing verification of various green building programs as well as consultation services. So we're really lucky to have these two here. Before they get started, I'm just going to do a brief overview of the round 3 challenge that they will be helping to provide some ideas about from their field experiences. The round 3 challenge is focused on pushing the envelope with wall retrofit designs. We're looking for student ideas about how can we create better wall retrofit designs. This is a big issue for the industry. There are over 114 million existing homes that are older than 2009. This means that they were constructed previous to energy codes in many locations. And so the high energy bills they might have, or uncomfortable rooms, and perhaps health and safety issues are a big reason why we need to think about improving the wall retrofit design options that are out there for homeowners to choose. Your specific challenge or specific ask around this challenge is to use a base case house, single family home of 2,400 square feet built in 1975, and to design a wall retrofit product that will meet the local code. You design what code you want to pick. Perhaps it's the location where you grew up or where your school is located, but you need to designate that. You need to address material needs, efficiency levels, air tightness, and that kind of thing. We also want to see you indicate demonstrated performance for moisture and air tightness requirements, as well as improved energy performance. So today's webinar, we will be getting into some of the field experiences around trying to address wall retrofit currently. So this is to give you some ideas about what you might think about. And as that little explosion there on the slide shows you, these ideas are due by midnight on February 22nd. That's 11:59 p.m. February 22nd. So with that, if Bill and Matt want to take themselves off of mute, I'll go ahead and run your slides.
All right. Thank you so much, Caroline. My name is Matt Waring. Caroline did a great job introducing us. Thank you so much. We're really pleased to be a part of this Jump into STEM program and this challenge specifically. I think that there's a lot of opportunity out there, and I think that's a good way to look at it. It's a challenge, but it is there's a lot of opportunity for improvement. So I'm hoping that we can give you a little context on that moving forward here, and also kind of show you what we deal with day to day in the field trying to address these types of issues. So yeah, let's hit that next slide, please, Caroline. So quick background about Veridian. We are a local 501c3 nonprofit local here in Richmond, Virginia. Our flagship program is the Earthcraft Green Building Program. It's a points-based green building program, much like LEED or your other green building programs. We are specific to the Southeast. We work on multifamily, single family, light commercial, and we also have a communities program. So we have a range of programs under that Earthcraft banner that we institute. We primarily work here in Virginia. To date, we have certified upwards of 23,000-ish dwelling units across the state of Virginia, a little bit in Maryland, and in the DC area as well. So that's a little bit about our organization. We've been in Richmond since 2006. So next slide, please. So here's Bill and myself, so you can get a visual on us. Bill standing there in front of the flux capacitor, about to do a little time traveling. No, that's our blower door. That's a light commercial enclosure test that we were doing up in Northern Virginia, and then I'm just boring in front of a tree. But we're your presenters today, and we hope to give you a little background here and some additional information on the building science behind what we're trying to do. Next slide, please. Thank you. So today, just a quick overview of what we're going to be going over. I'm going to give you some context about climate zone, kind of where we are in the construction industry with regard to this issue and the challenge in front of you, and overall just kind of construction as well as physics and buildings, and then design decisions and real-world strategies about how this is actually accomplished in the field currently, which I think you'll find to be interesting, but also not ideal, which means, again, ripe with opportunity here. Next slide. So some historical context. I'm actually a history major, and so this jumps out at me always. I'm not using that major now, but I'm heavily interested in building science, and I always think this is a very interesting slide. So you can kind of see overall energy use split there in around the 1960s. And residential buildings end up becoming quite a bit more, residential and just buildings in general, become quite a bit more energy use intensive. And so the real reason for that is space conditioning and the introduction of space conditioning into buildings around that time period, and it becoming more commonplace in the residential industry. So as we start using energy to condition the spaces that we inhabit, our energy use kind of goes off the charts, whereas some of these other sectors have really stayed pretty pretty level over that time period. And so this is not a super up-to-date slide, but I think that you can get the historical context of why this is such a big issue and how much energy we really are using in these homes. So yeah, next slide, please. And so to kind of build on that, Caroline mentioned briefly that, many of these 1975 homes and before were built to little or no energy code. I think looking at this, I pulled this directly off of energycodes.gov. This is as of December 2018. So you can see how many states are still behind on overall energy code, as well as how many states really do not actually adhere directly to an internationally recognized code. So, if you can see this in 2018 or 2019 and say, wow, it's kind of, a hodgepodge of code out there. Well, think about what it was in 1975 and how much it really was more or less the Wild West. You could get away with kind of murder with regard to overall buildings and what went into them. There were kit homes at that time, people building their own houses. So there are a lot of variables out there in construction type, but I think again, this really highlights the opportunity across the nation to improve upon existing buildings. And I think Bill and I both are in agreement that renovation is kind of the greenest form of construction in that all of the resources are pretty much right there in front of you. It's not cultivating new resources in order to kind of maintain or retrofit a single family home that's existing.
For sure.
Next slide, please. So I think in the challenge, it kind of outlines where, that you should be, or ideally you are going at this from a climate zone with which you are familiar. So where your university is located, I think is how it's worded in the challenge. This is just a good kind of visual view of where the climate zones kind of fall within the country. We are right there under that star here in Richmond, Virginia. We like to think of it as one of the more difficult places to build. We get a little bit of Maine and a little bit of Florida throughout the year, just kind of depends. But we build differently in different climate zones. So, addressing this issue from a different climate zone, say from Maine, would be different than how someone in Florida would address the same problem. So I think that's important to note. One thing I'll just add to that is that, here in Virginia, if you're on the Eastern Shore, you're in one very distinct climate zone. And if you're in the tip of Virginia out west, you could almost be in climate zone 5 there. And really, some of these lines are a bit arbitrary. So, the flexibility of being able to use a product or, retrofit a home with a product across many different climate zones and many different building conditions is very important to us and what we do, even just in the state of Virginia. So I think that's important to kind of take into account and understand that is something that, you're watching HGTV. We're not putting plastic in our walls here, but you might be doing that in Maine, putting a vapor barrier, a class 1 vapor retarder in a wall system. So these are all things that, would have to be addressed in a retrofit scenario. Next slide, please. So quickly, I wanted to highlight, and then you can hit the next slide. This is just the table from the 2015 IECC R value requirement. So you can see there in the red box highlighted is the R value per climate zone. So again, highlighting the fact that by climate zone, the R value requirements from a code perspective are different. And that makes sense. I mean, you're going to want more insulation, thermal protection in Maine than you would maybe in the middle of the country here in Virginia, just based on the range of temperature that you see. So obviously, again, you can see there the wood frame R value for an upcoming building here in the state of Virginia is R20 or R13 plus 5. That plus 5, where you see that, is a continuous insulation value. So an external to the wall system insulation value is something that would go behind a cladding, not in the cavity of the wall system. So that's how you read that. And that's all readily available. I think that we have some links here. We'll include that and get them to Caroline so she can include those links too on the website moving forward. Next slide, please. So having talked about sort of climate zone, and taking that into account when you all are addressing this issue, we wanted to kind of talk to you about the history, the climate zone, and then what we do when we look at a home or look at a set of drawings, and we move this problem out of the theoretical and kind of into the field, into the real world. And so, while you're thinking about the design of a wall and what it should do, I mean, essentially a good wall is an environmental separator. We build buildings to get inside from negative 60-degree temperatures like we're experiencing out west right now. So we don't have a lot to complain about. I think it's 40 here today, but at the same time, it would be a lot more difficult to provide this webinar to you all were we sitting outside. So, the entire intent here is to separate our internal lived-in environment from the external environment. And a good wall should have an air control layer, a moisture control layer, and a thermal control layer. We want to prevent draftiness, wind from blowing directly into the building. We want to prevent rain and bulk water from entering the building. And then we have to have some sort of thermal control, which is the insulation portion of this equation. So these are really the three main things that a wall must do in order for it to function properly. Next slide, please. So traditional energy retrofits typically focus on a crawl or a basement and then an attic. Next slide, please. And that is because these places are accessible. That is a big reason. It's easy to get into an attic and say, hey, I could add some insulation here. Whether that's to the roof deck or even to just the ceiling plane. But the same can be said about a crawl and a basement. Now, buildings' roots are really that crawl or basement. And so due to stack effect, much of the air in a building does flow upward and out of the roof assembly or through that ceiling plane. So, both of these are very effective retrofit strategies. But if you look at that simple drawing of a house, if you look at that in terms of a beer cooler, the top and bottom of a beer cooler doesn't do anything in and of itself to keep your beer cold or your sodas cold. You guys are 18, but if you think about it that way, it works the whole house works as a system, and that's the way we approach everything. All of these components work together, and so by completely ignoring the blue square there, we're really missing a lot of opportunity. 4 sides to our 6-sided box, where retrofit is a possibility, even though it may be a more difficult possibility. Next slide, please. So what we kind of talked about before kind of goes hand in hand with the very fundamentals of building science and physics in general. And so when we're talking about building science fundamentals, it really is kind of basic physics, high school level, college level physics, right? It's the movement of heat, moisture, and air. So if you click that next one, the movement of heat in a building is very important, right? We want to keep the interior temperature to about 70 degrees. Caroline, if you don't mind hitting that next slide. So, the same forces for heat movement work in a building as they do in anything else, right? Conduction is heat moving through a solid material. Convective loops are present in all homes, and we'll talk a little bit about that in wall systems. And then radiant heat. The best really example of radiant heat is just the sun warming the earth, right? So these are all things that are happening in the built environment and that we need to control. We're either taking heat out of the interior space or putting it back into it in the winter like we're doing now. Next slide, please. And just as important is the movement of moisture within a space. And maybe more so in some instances, this is the one, moisture and moisture problems in buildings are one of the largest drivers of cost overall in buildings in the country. I think there are staggering stats with regard to building failures, component failures, and building failures in general as they relate to moisture intrusion in buildings. And so 1 is bulk water there, 2 is capillary action, and 3 is infiltration. Air infiltration. Air is a moisture transport system. And that's something we're going to talk pretty heavily about here as we keep pushing through there. Bill wants me to talk about number 4 because that is inward solar vapor drive. And that just makes us sound very smart. But when water hits the side of a building and the sun comes out, you have 2 forces, both heat and air, moving inward into the building. So heat and moisture, rather. And so heat and air and moisture all move the same way. They all move from areas of high concentration to areas of low concentration. So nature is seeking an equilibrium. And so all of these three components need a driving force, basically. One very wet area, and then that wet area wants to move to more dry areas. That's just how water works. The same thing with heat. So, all these kind of fundamentals are important to take into account when you're thinking about overall design decisions with regard to wall retrofits and how the system works as a whole to keep all of these components in or out.
Yeah, and to quote somebody, much more intelligent than myself in this field, there's three things that destroy a building, and it's water, water, and water.
Yes.
So those are the things you want to be on the lookout for.
That's exactly right. That's great. Next slide, please. So why moisture is important. This is 7-year-old framing, and this is really torn up because of moisture intrusion into the wall system. And so, mold, mildew, organic growth, these things are very important to health and safety of occupants, right? People in buildings is what we should be designing around first and foremost. But we build buildings out of mold food, organic materials. And every day somebody comes up with a new material that we input into buildings that works for the same purposes. But the majority of our buildings are made out of wood and paper. And these things are mold food. So, as you start to increase the moisture content in a small enclosed space, you will get organic growth, and that growth will just feed on the actual material that you built your building out of. These are the things that we try to avoid every single day so that we don't run into these type of issues. And it really is not in a hot, humid environment like we find ourselves in here down towards the eastern part of the state in Virginia and much of the country. This can be a gigantic problem. If you're in Arizona, this may not be as big of an issue for you. But again, these are the biggest building failure issues that we see, and so we're kind of coming at this from our experience. Next slide, please. So thermal control. So for optimal thermal performance, what are we looking for? What's the goal here, right? Insulation should fill the cavity completely, like your hand fills the glove. Every cavity is a six-sided box as well. You want insulation to fill the cavity front to back, top to bottom, left to right. And that's what we grade insulation on 1, 2, and 3 levels. 3 being a pretty poor insulation install. So a grade 1 insulation is free from voids and compression. And should encase any infrastructure. You shouldn't have wires or plumbing, compressing the insulation as it's installed. This creates convective loops in the actual wall system, which degrades the overall R value of the actual insulation. So when I say that, I mean, if it's cold on the outside of the building, the air is more dense as it touches that exterior surface. It falls to the bottom of the cavity. As that air works towards the inside, it actually warms back up and creates a loop, and that air rises. And so all the time, air is rising and falling in a wall cavity, which degrades the overall R value of that insulation. So you may be paying for an R19, and you may be getting an R5. So, install quality is a huge issue and something that is definitely more difficult in a retrofit scenario. In many retrofit scenarios. Ideally, an insulation product would have high thermal mass. Great sound attenuation. You want it to be quiet in your house. You don't want to hear every siren and person walking by. And permeability in wall systems for us especially is a very big issue, which we just kind of talked about. But we know these buildings are going to get wet, right? They get wet during the life cycle of the building. They also get wet during construction. So, water is going to get in, but we have to be able to have it dry. One way or the other. So these are all very important aspects to kind of take into consideration when we're talking about insulating or re-insulating a building. Next slide, please. Just a quick rundown on how insulation works and like weighted R values. So, we have a bunch of wood in the wall system, and that is R1 per inch. So every 3.5 inches, it's R3.5, and then in between that cavity you get R19. So, overall there's a weighted average for the R value of the system, and that's an important thing to remember. So small gaps and voids make, it's like you go and you have 5 tests and you get 4 100s and a 0. And somehow your average is a 70, right, in the class, even though you got a bunch of hundreds on tests, right? Well, it's the same thing. Insulation and the overall coverage of insulation works the exact same way. R38 installed in a roof or an attic system with 5% gaps drops that overall R value to a R27. So again, you're paying, your homeowner or your client is paying for R38, and they end up with an R27. So a 30% reduction in what they're actually paying for. So just a quick rundown. R is just resistance to heat and flow. A U value is something that an assembly gets, multiple materials, and that is just the inverse of an R. So 1 divided by the R. And these are just the two ways that, like, a Windows system will get a U value, an insulation product gets an R value. So just things to remember. Yeah, so I think that's the majority of that stuff. So yeah, next slide, please. Yeah, so I'm gonna let Bill take over here for a minute, yeah, I think the important thing to remember here is just one, the historical context is we're ripe for change here, and two, you will see what we have to do in the field here, what it takes in the field to actually get some of this stuff done, and that's really where the rubber hits the road.
Right. Cool. So you've got a bunch of different insulation types at your disposal here when retrofitting a wall. All of them have different characteristics and can be used in different applications. So foam, comes in a couple different varieties. You've got spray foam, and you've got a rigid board that can be used. The rigid board comes in a bunch of different types. It can be, it's XPS, EPS, and polyiso. Those are all great for exterior applications, whereas spray foam, is great for hard to reach areas and comes in two different varieties. That's open cell and closed cell. So open cell foam, like it sounds, it's more expansive and is often water based. It has a lower R value than its counterpart, closed cell foam. And so closed cell foam, it's very dense. It's great for achieving air tightness and has high R values, but it has a very low perm rating. So that's something to consider. Cellulose is just chopped up recycled newspaper, probably my personal favorite insulation out there, but it's okay to be a little biased. Fiberglass, that can be, that's just like it sounds. Little glass fibers that get blown across a mesh screen, and that's how it's made. So that can be blown in or is in a bat as well.
That's probably your most common insulation product that we see on the market still, and comes in blown and that being a little bit more difficult to install properly.
Yeah, if you're unfamiliar, it's that little pink stuff you see in walls all the time. So, and then we've got rock wool, which I believe is a brand name, but it's mineral wool. It's made from slag. That's an interesting product because it comes in a board form as well, and it's hydrophobic, so it actually repels water. And next slide. So, one of the most important things is, a site examination when determining your work scope. This is probably one of the most determining factors. And so walking the exterior of the site can give you a great idea of what this project is really going to need. And so one of the first things to look at is cladding type. If it has siding versus brick, that can really change your scope for your retrofit. You want to look at bulk water. So we're looking at site grade to make sure that you have positive flow away from the foundation. Any sort of negative slope around the foundation is going to really invite that water into the foundation. Looking at gutters and roof overhangs to make sure that water is properly discharged. House orientation can play a big role, and similarly with surrounding vegetation. If you're driving around and you see somebody's roof covered in moss, that's just because they're not getting enough sunlight and there's not enough drying potential on that roof. So all of these things can play a huge part.
Right, and so for your challenge, a lot of this you don't necessarily have to take into account, but in the real world, these are all things that absolutely have to come into your decision tree when you're making these decisions and trying to move forward with a good, healthy design for both the homeowner and the home itself.
All right, next slide. So here we've got a little fancy tool that we like to use in the field. It can be extremely helpful, but it's thermal imaging, and it can be used for a variety of things in the field. But on the picture right here, what you're seeing is a void in the insulation of this home, and so you can actually see the studs in each individual bay running vertically, and then you've got that bright hot spot in the middle that's showing where it's uninsulated.
Right. You can also, just of note, I think, is the kind of thermal loss around the windows and the fenestration in this picture. It's just always kind of jumps out at me. Is how much loss you get around those window openings. So again, a weighted R value, weighted U value of the overall assembly is important.
Right.
Trying to improve the overall performance of the project.
All right, next slide. Cool. And then along with the exterior site assessment, you got to take, at least we have to take the client goals into account. And so, budget is often probably one of the largest concerns. We want to make sure everybody gets a good return on investment on the work that's done. But then comfort is a serious concern. If someone is, sometimes you get those large discrepancies in temperature between the first and second floor. That can often be remediated by, air sealing and insulating the attic plane. So those are important things to take into account before you decide on a scope. And then intrusiveness, if somebody works from home during the day but wants to improve the performance of their home, but they can't interrupt their work schedule, then that can play into the scope as well. And then lastly, indoor air quality can play on scope if you have anything to...
Yeah, I would just say, goals of the renovation, I don't want to gloss over that too quickly, in that, a lot of what we do is focused around, obviously budget, but, homeowners have specific goals. They want to be able to use, that bonus room in their house or that ancillary dwelling unit. They have specific goals. And so it really helps to narrow the scope of what you're trying to do and hone in on what the actual problems are for the homeowner, because client satisfaction on the back end is important for everybody, right? So, this is just real world stuff that we deal with day in and day out. And if the homeowner is happy with the house they're living in or is unhappy currently, you can help them be happy. That's an important aspect of what we do. Indoor air quality, I think this challenge really does a good job addressing the moisture concerns and wanting you all to focus on the moisture concerns. This, basically organic growth in buildings is a huge concern from a health and safety standpoint for homeowners. So again, we just can't hit that enough.
And next slide. So here we've got our first real world example. This is probably, the highest cost strategy that we'll be showing you. This one, the homeowner desires the ability to keep as much of the existing house as possible. It is a pretty intrusive strategy. So, what ended up being done is that the cladding and the sheathing along the exterior was completely removed. And what he's doing, he's spraying closed cell foam into the wall right now. So that's, you're getting a nice air tightness from the closed cell foam. And that's actually going to be paired with some fiberglass insulation available on the next slide. So I guess, and I'll talk into the next one as well. So this section of the home was then re-sheathed with this sheathing, which is a structural insulated sheathing. This combines the insulation with the sheathing, reducing labor costs, and which is often more used on new construction. But see, from behind, we've got the closed cell foam in the wall. We've got the unfaced fiberglass bats on top of that. It's kind of a tried and true method in the field, just called the flash and bat. And it's a great combination between the products because it relies on the air sealing of the spray foam, which then improves the thermal performance of the fiberglass bats.
Right. Yeah, Bill, they added a layer of, so in place of OSB, they used structurally insulated sheathing on the exterior to prevent the thermal bridging. So we saw some thermal bridging in that thermal camera image, and that's what we refer to when you're talking about the low R value of a piece of framing member, like a wood stud. So they reduced that as well as included all of this insulation into these cavities, which was not there prior to. And how did this thing end up on the back end, Bill? performance-wise? It was near zero, wasn't it?
Yeah. So yeah, we like to call it a near zero energy remodel. But it was tied with new HVAC system and solar PV on the roof, which reduced the electric bills to about just an $8 service charge per month for the year.
So, right. So obviously something that works very well, but this was a full-on, more or less, gut rehab.
Yes.
What drove you to this strategy, I believe, was the desire for the homeowner to maintain as much of the existing structure as possible too.
Right.
She wasn't living in the space, but she didn't want to throw a bunch of plaster in the trash if we didn't need to.
Yep.
Right. Cool.
All right. Next slide. So here we've kind of got mid-cost, low intrusiveness on retrofit opportunities here. And kind of one thing that drove us to this is that, the cladding needed to be removed anyway. You can see the old cladding on the side, and which provided a good opportunity to wrap the entire building in exterior continuous insulation. And so, one thing we hear a lot in the field is that, it's strange that we stuff insulation into stud cavities and rely on that completely. You don't stuff a sweater between your ribs when you're cold. You put on a jacket so that you're completely encased in insulation. And so really the industry needs to move towards more continuous insulation across the board. So, and just kind of covering some of the, this photo was taken partially through the renovation. So there's a little gap in the insulation there pictured right. You just want to make sure that your insulation is as continuous as possible, and all these seams in the insulation should be taped as well.
Right. And then just like to kind of hit on the point of, new material meeting old material and depth issues with regard to adding continuous exterior insulation. I mean, all of these, from an architectural standpoint, all of these materials need to be able to be married up to one another and show as a kind of contiguous exterior cladding system on the back end that is aesthetically pleasing. So you can't just bump out 3 inches of foam and not have some way to address that transition back to other cladding if you're not doing this to all 6 sides of the building or what have you. So, again, design decisions, it's all got to be taken into account. The whole thing works as a system.
All right, next slide. So here we've got, this was some exterior insulation that was done along the roof line. The reason for doing this was that the homeowner wanted to kind of maintain the aesthetic from the inside as much as possible. So
had an exposed beam,
yeah.
Cathedral ceiling on the interior, and they didn't want to go and stuff a bunch of insulation into a very pretty interior ceiling, but they did want to move the dew point to the exterior.
Right.
So that's something we could probably hit on here on the back end too.
Yeah, so we ended up removing the entire roof, re-roofing the entire thing. So it's covered with 4 inches of polyiso cyanurate, which is one of those rigid foam insulations that I mentioned previously. And it provides a great example of, a good installation for exterior foam. You want to make sure that all those seams are staggered and properly taped.
Both horizontal and vertical seams are all staggered. 2 layers. They have all their underlayment already laid down there, and then the actual roofing goes back over top of that on the back end.
All right, next slide. So this is kind of one of the most tried and true methods for retrofitting an existing wall. This one, we're doing it from the exterior because, like I mentioned earlier in the slide, the homeowner actually, she worked from home and so didn't want any sort of intrusive work scope. So we're lifting up existing aluminum siding, drilling through the sheathing from the outside, and then filling it with cellulose insulation. And this is a, fairly low cost solution and can be pretty easy to do, especially, that we're doing this in Vermont winter. So it's not.
Yeah, it just is going to depend on your cladding type too. I mean, most lap sidings you can get this much play in. This is aluminum, so your hardies you're not going to be able to really pry up, but so hard on a hardy plank, so
Right.
Or like a cementitious kind of cladding. So it all plays into the building type, and they were able to do this, and they executed on it well. But that's not always the case. If you have a brick home, there's no way that you can do something like this.
Exactly. And last slide. So again, this is another drill and fill technique. This one is just done from the interior. And so, this has been traditionally limited to cellulose, but can now be done with fiberglass insulation as well. And it's an extremely cost-effective solution. So it's, just for example, this work scope, we ended up cutting a perimeter hole around the entire home along the exterior walls and removing existing fiberglass insulation. And so fiberglass insulation does nothing to impede the movement of air, and it can actually be seen. There's probably some great examples out there that you can see, but it acts as a filter, and so we were able to see where all that air movement was through the cladding and the fiberglass. And so before all these projects, this is probably one of those ones I'm most proud of, but, we blower door test before we go in, and we were completely unable to depressurize the home. And it was estimating probably about 12,000 CFM of leakage, which is extremely high. And so after the work scope, we brought the attic into conditioned space, conditioned the crawl space, and then re-insulated every wall cavity with cellulose insulation. And by doing so, we were able to drop the number to 4,000. So quite a big jump there.
Yeah, that's awesome. And so a couple of things just to kind of remember when we're talking about this or any other kind of drill and fill scenario is, again, ensuring that there are no bulk water issues in those wall systems. Just adding insulation to that is not going to help solve any sort of bulk water issue. And then I think the good thing about this, I'm sure there's a way to do this with the spray foam, but I think the good thing about this is, one, again, cellulose has very high thermal mass. It holds its temperature very well, good sound attenuation. It's a recycled product. Everything that's on the floor there at our installer's feet gets sucked right back up and put right back in the truck and reused on the next job. So, there's very little waste. It's all recycled material. They actually take down the pieces that they cut out of the wall system and they put them right back up, drywall mud them back up, and there's no need to go in with new drywall. So this is a very good way if you're able to get in and work in the house and you're not working around people's things. That could definitely still be an issue. And there's still a way to do it otherwise, but this will encase all of your infrastructure. This is a very good way to re-insulate a house, and that's kind of the reason we wanted to end on it. It really is the most success we've had in this kind of retrofit of wall insulation market. I think Bill did a really excellent job on this house, and the homeowner was extremely happy on the back end, which I think was one of the most important things from where we're sitting. So I think that's all we had for you all today.
Yeah, I think that wraps up.
We'd love to answer any questions anyone has.
Yeah, great. Thank you so much, Bill and Matt. Really interesting things that you have here, the examples you've been doing up and down the East Coast, and some scary scenes of moisture damaging the walls. So we definitely want to avoid that. If anybody has any questions, go ahead and type those into the chat field. And while I wait to see if any come in, I'm going to ask one. I think you talked about this on the last slide a little bit, but how do you determine the energy performance? Say you've come up with a wall retrofit solution you're thinking about. How do you know what the energy performance of that solution or strategy is going to be? What ways do you have that in the design process, and then perhaps once you're implementing it in the field?
Yeah, so we personally, we're all HERS raters here at Meridian, or working towards that, and so we use Ecotrope, which is a ResNet approved software, and that is our primary energy modeling technique. There are a lot of free softwares. Beopt, I think, is one of the best out there for kind of overall optimization of building energy, and so you can kind of use scenarios like that in the design process. We find that it's good. And this is true of a lot of what we do, but it's good to offer our clients several options, kind of one middle of the road option that is going to effectively address their concerns, a kind of higher end option, and then hit them with a low option and let them kind of make the decision on their end which one they want to move forward with. But we like to put that information in front of them on the front end. And so, we know that we can get about R13 from a 3.5-inch cavity. And so we can model this home with no insulation, with very poor R11 fiberglass insulation, and then, also move it up to spray foam, R6 per inch, or we can move it all the way through all of these things pretty easily once we get the overall structure of the model built, and then make a value decision based on overall cost per square foot, and the energy savings used. That's a great question, and that's definitely something we think should be utilized moving forward. Not every contractor has the time to do that, but we do try to use those design tools that we have at our fingertips. And maybe we are a bit jaded in that we have a lot of access to modeling software around here. But that is something that I think is extremely important, is kind of understanding the value proposition of what you're doing and the return on investment. Neat and Mia, I think, are two other softwares just that are great for providing an ROI, a return on investment calculation, for overall cost. I think RS Means is also a great way to kind of get overall construction costs, per square foot for your general area. So there are databases out there that I think you should have access to kind of get that information for install costs, for different products, different types of construction.
Great. Yeah, and then I was kind of wondering, similarly, so that was energy performance, but you emphasized quite eloquently that addressing moisture is important. Are there tools to help ensure that you're choosing products and materials that are going to be the best for managing moisture, and how do you determine that?
Yeah, that's great. So, there are modeling tools for almost everything. Wolfie, I think, is one that does dew point calculations. So you can do a fairly easy dew point calculation, on the back of a napkin, and you can find that equation, just Googling it. But they have very sophisticated software out there. What was not Wolfie? What was the one that?
There's a German tool called UWERT. It's U-WERT that lets you build a hydrothermal model of a wall. So
right.
It's a very helpful tool.
Right. That's also a great tool. But, dew point calculation, basically, just to kind of give you a quick broad overview of that and give the students one, is if you put a glass of water out, a cold glass of water, it sweats, right? The same is true of all building materials. If you're hitting the backside of a warm cladding with a whole bunch of cold air, well, then it's going to eventually end up being a condensation plane. And that can create moisture within a wall system without actually ever having bulk water. So it's that air as a moisture transport system kind of philosophy. And so, these tools will definitely help you understand how those different materials will react to different levels of moisture in the environment. And you can kind of get a ballpark understanding of where the relative humidity has to stay in order for you to never hit that kind of condensation point within a wall system. And so you can use your kind of climate data in your own space to enter into this model, and then it'll help you understand what level of insulation you need to get to prevent theoretical condensation within that wall system. I think UWERT is a free, is that? Yeah, so UWERT is definitely a free software. And so that's something we could probably provide a link to on the back end. We'll shoot you, Caroline.
Okay, great. And then a question that came in that's looking specifically at blown-in cellulose. Do you have to remove the existing insulation material if you decide to do blow-in cellulose into an existing wall to improve the insulation? And if I can add on to that question, if you were using a different technology other than blown-in cellulose, similarly, do you remove the existing insulation? What do you do with the old stuff, basically?
So, me personally, I would remove the existing insulation, especially when, dense packing cellulose, and, specifically back to that farmhouse example, when you dense pack cellulose, you're looking for a certain amount of square feet per pound, I believe, or density, a certain density for the insulation. And so if you achieve that density, then you're able to, it can act as an air barrier. And so that's probably one of the main things we're looking for with the cellulose. But also, if you remove the old insulation, you're going to get a better installation, which is going to improve the thermal performance.
Now, do you have to? No, not necessarily. And I do have like maybe one kind of conjectural point on that, in that I live in a Cape Cod, and in order to insulate the knee wall area transition into the attic space, one of our best installers here will leave a bat in place and press it down, and then run their foam gun down this kind of slope embankment that's otherwise inaccessible. And then they leave the fiberglass there on the back end. I mean, it's more of a flash coat. They're doing maybe a couple inches, but they don't necessarily have to pull that back out of there. It's not going to hurt it. But when you get a bunch of fiberglass insulation that's full of a bunch of dust, I don't think it's ever a bad idea to get rid of it. Do you have to? No.
Yeah.
Now, if it's sustaining some sort of moisture growth, or you find that on the first couple, then maybe it's smart to go ahead and just start pulling it out.
Great. So one last question before we close things out, but have you guys used, or how do you consider the option for insulated siding in your retrofit strategies?
Yeah, so I have used insulated siding on a project. I've worked on a reno project in the past. I don't mind that, though. I don't think it's as contiguous as I would like from a continuous exterior insulation product. I really like a hard board being directly nailed, without the lap sort of to it. So typically a siding product like that would have a lap, and therefore almost a space in between each one. Continuity is a very important thing when you're talking about insulation, as well as an air barrier. Now, I like an insulated siding product. I don't hate the idea of combining two products like that, but typically, one's purpose is insulation and the other's cladding and aesthetic. Mm-hmm. So my personal opinion is it's easier to get the water sealing and air sealing details correct by not having a combined product. Now, adding that over 1 inch of, if you wanted to get to a higher R value, you have 1 inch and depth issue. I mean, there's definitely nothing wrong with that. We're always in favor of more insulation rather than less. As far as modeling performance of a system like that, I don't have a lot of information on that.
Okay, great. Well, I really appreciate all the wonderful information that you've provided today, and I will gather the links from you and add them to our website. Up on the screen right now is where these pieces of information will be provided on a card about the Round 3 challenge. And if you scroll down, you'll find the recorded webinars from the first 2 in this series for Round 3. And you will find today's webinar there as well, and the links that we just talked about. So do check that out and send in your ideas by February 22nd. We're really excited about this challenge. This is your opportunity to compete for those internship slots and join in that festivity out in Denver, Colorado. So jump.ideascale.com is where you need to go. And if you have any questions, there's a question field there. And thank you so much for joining us today. Bye-bye.
Thank you. Thank you.